Sana. I'm from Chennai Institute of Technology. I'm currently pursuing electrical and electronics engineering. So my team is Shishi Hari Shango Kaisa. So their problem statement is to promote smart farming agriculture practices in India. So I'm currently solving a problem called soil testing. So in India, there are around 100 million farmers. So each farmers, most of the farmers in India have 1 to 2 hectares of land. So in these lands, they need to take soil test samples, soil test. They need to conduct soil test, which are the most of things that they test for are nitrogen, phosphorus, and potassium. So they do the test by collecting the sample. They will transport it to the lab. In the lab, they will do the testing, and after that, they will generate a report, which will be sent to the farmer after a week. So in order to reduce this cost and reduce this time, what I am proposing is a smart, low cost portable sensor that the farmers themselves can buy and directly measure on the land itself. It will give the results within seconds. So this is what I'm currently proposing. You might ask, what are the existing products that already do this? So in India, in the market that I have researched, there are only chemical existing setups which can take only 5 to 10 samples, and these kits cost around 3,000 rupees. So other than that, other than chemical methods, there are electrical sensors. But these electrical sensors, the sensors themselves, which will have its own connector, the sensors themselves cost around 3,000 rupees. They are not portable devices. Moving forward, the fully functional portable devices cost around 20,000 rupees, which is not at all affordable by farmers. So what I'm proposing is a mm, moderate cost, around 2,000 rupees, a sensor that they can use to take multiple repeated samples of the soil, and it can deliver the NPK values. So how I'm doing it? So how this system works? Instead of directly using the sensors, what I'm doing is that I'm using something called SINFER. SINFER stands for Soil Inference System. It is a bag of mathematical relations that relate different soil parameters. So one of these relation uses pH and conductivity in order to find the NPK. So with this relation, we have developed a small portable device that has pH sensor and electrical conductivity sensor. With this measurement, we will calculate the NPK, nitrogen, phosphorus, and potassium values of the land. So this drastically reduces the cost of the sensor, the cost of the portable device. The portable device itself has an OLED screen in which it will show the results immediately. This portable device can itself store about 50 data points, and it can provide a summary of the result, a summary of the entire land, about how much average NPK values do they need to buy. So other than that, so this is a portable device which I have built. This is a sample device prototype which we built and tested in the tested. So this prototype currently consists of Arduino and OLED displays. We are planning to move into our own custom PCBs and tightly integrating with the sensors, doing a full vertical integration. This portable device, we are planning to cost it around 2,000 rupees. That is affordable by farmers that they can use to take multiple samples. So taking multiple samples for micro fertilization is a tremendous feat, right? So it might take an entire day in order for the farmer to go directly and take the samples, because every 2 to 3 meters the NPK values will automatically change. So in order to avoid that, we are doing a mobile robot. This robot, we are planning to do it as a simple robot under 10K, under 10,000 rupees, that the farmers can buy and can send it to the land. So this robot will automatically collect the NPK values data and will automatically upload it to the app. So this is our sample app. In this app, we can select our end land, and we can send the robot. The robot will collect the pH, moisture, and all those data, and it will directly tell it in the apps itself. So in this app, let's say the user wants to grow a rice. So after scanning with the portable device or with the mobile rover, the app will tell how much NPK fertilizer do they need to buy more in order to grow that specific rice crop. So let's say they need to grow something like lettuce. So in order to grow lettuce, they need to purchase this amount of NPK fertilizer in order to grow lettuce. So like this, the app itself will give recommendations. Based on it, the farmers can buy the fertilizers. So other than that, we are also adding an optional feature for the farmers in order to collect data. So with this NPK data of their land, we can get a sense of how the NPK distributes over time in the entire region of India, with which we can accurately train our own models, and we can directly do an OT update for their farmers devices, which will automatically improve their devices as well. So how it's feasible and viable? So after taking numerous surveys, we found that most of the farmers in India do not have electricity. Electrical sockets where in which they can plug and charge their systems. So what we propose for the portable device is a inbuilt solar panel system, just like a calculator. It can charge directly with the solar sunlight itself. So it will eliminate the need for charging and need to carry chargers and maintenance of it. So the next thing is connectivity and data transmission. As I mentioned before about the rover, my, most of the farmers do not have Bluetooth enabled smartphones. So for them, we are using normal mobile communication LTE around 2G. So with which the robot itself can send the data via the to the cellular network and can send it directly to the phone or via a phone call. A remote worker can extract the data and directly tell it to the farmers. This can also be automated with an automated voice call itself. So we also provide in our app a multilingual UI covering almost 200 Indian languages for these farmers. The next is the impact and benefits. The impact and benefits for both Japan and India. So for in India, we have the huge amount of farmers market who are in need of these solutions in order to do their savings. Because in India, for 2 hectares of land, it costs around 10,000 rupees of fertilizer. So for the fertilizer itself costs around 10,000 rupees. So by using these devices, they can minimize the cost to around 2 to 3,000 rupees. This is a huge saving for farmers. So for farmers in India, we are doing this, and for Japan, all the sensors here, the microprocessors used in these systems come from Japan, and other than that, the manufacturing systems from Japan will be utilized for production of these systems. So this will ensure a better world for all of us and for the future. So the thing that I like about more about Japan and why I'm doing it with Japan is because of the lean manufacturing system. I've learned a lot about it. I've read the Toyota production system, the lean startup, all those books that are from the lean manufacturing and the 5 years systems, Kaizen, all these production systems that are being evolved in Japan is just extremely efficient, and it's been almost used in even in Indian industries as well. So this is what most inspires me about Japan is their work culture, their thought process. Of these production systems, which I'm also trying to implement in my own life, about the 80-20 power law rule. Most of it actually came from Japan. So I'm ending this presentation with a note for thanking you. I'm really grateful for this opportunity, so that I can, with this opportunity only, I got to know about all these problems that the farmers face, and about all these things. So I'm really grateful for this opportunity. Thank you. Thank you so much.